So this video is going to go through some practice problems. So this is under, this packet is practice mass spec, and kind of point out the things that you need to look for. And for this, you need a calculator. So make sure you have a calculator handy for this discussion. So there's many different ways of using mass spec. We're going to use it for one purpose, and that is to find what we call the molar mass peak at the end here, and it's the +1 peak. So what I have labeled on these mass spec is this number, this last peak essentially, or stick, is the molar mass peak for this molecule. So it tells us the overall molecular mass of that molecule. So we have the relative abundance here, mass per charge ratio. So all of these sticks have meaning to them because some, and I'll explain that to you in another example, there's other purposes than just finding the mass. So scientists use this for different ways. So if you would please write down, I will make this a little bigger now that we have that peak. I'll write down 87.5% carbon and 12.5% hydrogen. So these mass spectrophotometers give us these percentages. So what I'm going to show you is how to do an empirical formula calculation that we've done before, more traditional way, and then I'll show you a different way of approaching it. So you take the 87.5 and change it to grams, and take the 12.5 and change that to grams. And then the second step is to, of course, divide it by its respective molar mass. So we have carbon is 12, hydrogen is 1, and we get this to moles. So we get 7.29 moles of carbon, and we get, of course, 12.5 moles of hydrogen. So we divide it by the smallest of these two numbers. So again, this is 7.29 divided by 7.29, and I get 1, and this one I get 1.71. Okay, so not very nice numbers. So I need to multiply this number by something and get it to a whole number. So what you have to look at is my overall mass is 96, okay? And if my mass of carbon is 12, I got to think, okay, well, if I multiply that by 5, that's going to give me 5 times 12. That gives me 60. That's not a high enough. If I multiply it maybe by 7, 7 would give me like 84. That might be something I want to think about. So one way you could kind of rationalize it is, okay, what's the number I need to multiply it by to get it to a whole number? So sometimes you might have to like play around with it, and I'll show you a different way of approaching it as well. So carbon turns out to be 7, hydrogen turns out to be 12. So my formula is C7H12. And that makes sense because 7 times 12 is 84. And then if I take 12 times 1, that's of course 12, I get 96. So that is my formula from this. Now, another way you could do the problem, and this is again a personal preference, is you could actually take the percentages and figure out how many you have. So for example, if I take 0.875, so take the decimal, and I multiply it by the 96, that's going to tell me how much of the mass is due to the carbon. Well, it comes out to be about 84. Well, if I divide that by 12, which is the molar mass of carbon, I get 7, and that is how many carbons I have. And again, you could then take the 0.215 times the 96. That comes out to be, I didn't do this one because I kind of know what the answer is. It comes out to be 12, of course, divided by 1 gram per mole, that gives me 12. So that's 2 different ways you could do these types of problems. And again, it's a personal preference if you like more of the traditional way. So if you go to the next problem, okay, this one has a molar mass peak of 112, okay? So I'm going to give you, for this one, I'm going to give you the percentages, okay? So carbon is 85.72% is carbon, and 14.28% is hydrogen. So see if you could find the formula that gets you to a total mass of 112. So I'm going to pause the video and then come back. So I did it more the traditional way because I want to show you something. If you do it this way, you end up with a 1-to-2 relationship. The numbers actually come out very nicely. So you get a formula of CH2. okay, as the empirical formula. Well, realize that that doesn't add up to 112. If I add up a carbon and 2 hydrogens, that adds up to 14. So you take the 112 and you divide it by 14, and you find that the magic number is 8. And so then you have to multiply the empirical formula by that. So you get C8H16. Again, you might find it easier if you took 85% of the 112 and divide that by 12, you would get 8 a lot faster. So again, it is a personal preference which way you like to do it, but that is going to be, again, the type of calculation you have to do with the mass spec. So next one has a mass peak of 86, so that's going to be the mass total that you get. So for this one, carbon is 83.7% is carbon, and 16.3% is hydrogen. Okay, so 83.7% and 16.3. So see if you could do that. I'm going to pause the video and come back. So this one I used the percentage and just took the molar mass peak of 86 and multiplied it and then divided by 12 divided by 1. So I get approximately 6 and 14, which adds up to the molar mass peak. So you get C6H14. All right, so skip the next two just because we don't need to really look at that all that much. If you go to this page, I know it's not a great copy, but it's an example of a different way you can use a mass spectrometer. So some organic molecules get very large. And so since they get so large, sometimes scientists use this technique to kind of chop it up into little pieces. So if you look at the molar mass peak of 72 here, you also have some other peaks labeled, 57, 43, 29, 17. And then one that I want to talk about is 15. Well, what actually has a mass of 15 when you're talking about carbon? Well, it turns out to be carbon and 3 hydrogens, okay? So if you look at each one of these steps, some of them are a step of like 15. So if you look at this molecule, which is what the mass spec is about, if I take a look at, I got 2 CH3s, I actually have 3 CH3s that could be chopped off at different points. So that is a different technique that scientists use this for, especially if you get to really large molecules, that these peaks are used for other purposes. Again, all we're going to use it for is the molar mass peak. It is another thing that you can see. And one other thing, and this is for something we're going to be talking about when we go on our field trip. If I happen to have a halogen in my molecule, so one halogen that you're going to see is chlorine, the other one is bromine. This one happens to have bromine in it. Well, if you could see, most of the peaks are down here, but then you have 2 big peaks over here. And technically speaking, this is where the molar mass peak is. What you have are twin peaks. And that is indicative of what we call bromine. And that is because this is the M+1 peak and this is the M+2 peak, meaning you made a +1 ion versus a +2 ion. Again, we're not going to focus too much on it, but it's very indicative of bromine to have this because bromine has 2 isotopes. One is bromine 79 and one is bromine 81. And what's interesting about bromines, it's 2 isotopes. They're about 50-50. So that means their molar mass is about 80. So you get 2 twin peaks that are 2 apart because half of the bromine is bromine 79, half of the bromine is 81, and you get the similar size 2 peaks to show that you have bromine. Plus, if you take 80 minus 122, you get approximately 43 and so on and so forth. Similarly, we talked about this in the notes, you have chlorine 35 and chlorine 37. Well, you actually have 75% is chlorine 35, while chlorine 37 is 25%. Okay. So with this isotope, with this chlorine, if chlorine was attached to this molecule, you would not see the twin peaks like you have here. Because they're in a 3-to-1 ratio, you would actually see the 2 peaks being 2 apart like you have here, but one would be 3 times the size as the other one. And that's an easy way for you to tell if you have chlorine in your molecule versus bromine. So it's kind of an interesting phenomenon that we will see.